Alright, 4-6 is Advanced Algebra 2, doing some linear programming today. So what the heck is linear programming? Well, linear programming is a problem in which we want to find a solution to a system of inequalities that either minimizes or maximizes a linear combination of variables. So in real life, people want to minimize their cost or they want to maximize their profit. So when they say linear programming, it's not like they're talking about a computer, though. It gives a solution to a program or like a course of action to follow. So back in the day, John Baptiste Joseph Fourier proved this theorem called the linear programming theorem. It says that you can find either the maximum or the minimum of a linear combination once we find the feasible region, which is what we did last time, that area that we highlighted. So the feasible region of every linear programming is going to be convex, and the maximum or minimum is going to be at one of those vertices of the feasible region. So where in the real world do people use this? Well, we've got all kinds of examples today, but in industries, when competitors make the same product, like in gasoline or paper appliances or whatever, So basically, let's just get started. Here's the steps we're going to follow. It's a little overkill, so why don't we just dive in and swim? And here's what we got. It's going to seem overwhelming at first. It's really, really, really not that complicated. There's a large story that goes involved with it, so we're going to read through it. They're going to give us a ton of information, but really it's not too bad when we follow all these steps that we have listed out for you. So first, let's just read the story. We got the Built Right Furniture Company. They make wooden desks and chairs. Carpenters and finishers work on each item. On the average, the carpenters spend 4 hours working on each chair and 8 hours working on each desk. There's enough carpenters for up to 8,000 worker hours per week. The finishers spend about 2 hours on each chair and 1 hour on each desk. There's enough finishers for a maximum of 1,300 worker hours per week. And the company knows that they're going to earn a profit of $15 for every chair and $20 for every desk. Holy cow, right? So given these constraints, how much of each item should be produced to maximize the profit? There's the key right there. We want to maximize the profit. And what will that maximum profit be? Wow, that is a lot of information. Don't let it overwhelm you, because when we follow these steps, it's going to be pretty simple. And honestly, I'm a big believer in switching step 1 and step 2 around, but I didn't want to change the worksheet, so we're going to do step 2 first. We're going to identify the variables. And there's just going to be 2, right? This is a linear situation, so you're going to have an x and a y. There's only 2 variables, and where can you find those? It's real simple. You find the question, what they're asking you. They say how many of each item should be produced. So they literally don't tell you what they're looking for in the question, but they kind of do up here. Really, you got 4 things that they're talking about. You got desks, chairs, carpenters, and finishers. Well, they're producing items, and you don't produce carpenters and produce finishers. You produce desks and chairs, right? So those are the 2 items. Here on step 2, let's define those. X can be the number of chairs made, and Y can be the number of desks made. And again, if you need to pause the video because I'm moving too fast because I've got all this typed out already, pause the video to get that written down. But defining the variables is really, in my opinion, the first thing you should do, because then that's going to help you do step 1, set up a table using the constraints. Again, please don't let this overwhelm you. After 2 examples, you'll feel pretty comfortable to where we'll do 2 more after that. So to set up the table using the constraints, here's what we should do. Like whatever our variables were, one of them was chairs and one of them was desks, set up a column. We're going to set up a little table right here. So a column for chairs, a column for desks, and a column for total, right? So just trust me on this. It'll make sense after we're finished. The other thing you're going to put in your table is basically like the other ingredients they were talking about. We've already taken care of desks and chairs, but remember there was carpenters and finishers, because some carpenters are going to work on the chairs, some finishers are going to work on the chairs, and the same thing for the desks. So we're going to put those guys, carpenters and finishers, as little rows in this deal, and it's up to you if you want to make this into a real table or not. On the next few examples I'm not going to do that, but just a way to organize the data right here. Okay, so step 2 is really important, in my opinion, to do first. Figure out what your variables are. They're going to go up here at the top, right? They'll be your columns. And then all the other ingredients, they're going to be your row categories. And now we just got to go back and read through the problem and kind of like put in the information here. So let's just go through it. Blah, 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 blah. Nothing here. Carpenters and finished work on each item. On the average, the carpenters spend 4 hours working on a chair. Boom, right here. 4 hours working on a chair, so bingo. Carpenters, chair, 4 hours. And they work 8 hours on a desk. Bing, so they're still talking about carpenters and the desks right there. There's enough carpenters for up to 8,000 worker hours. So that's like your total information. Like that's how many total hours that they can put in there. So there's 8,000 in the carpenters total category right there. Then they give us a whole new set of information here about the finishers. The finishers spend about 2 hours on each chair, so finishers and chair will be 2 hours, and 1 hour on each desk, and they can work for a total of 1,300 hours. So really, the chart, the little table, I should say, I could call it a chart, but the table is very, very crucial if you know where to put all your labels, like chairs and desks. They go up top because that's what X and Y stand for, and the other stuff goes over here. Now there is information that we haven't even dealt with yet. We've got this profit of $15 for a chair and profit of $20. That'll come later. All your profits or your costs, like your money numbers, they'll come later. Okay, so we'll deal with those later. This is enough to get started to write a system of inequalities. And here, let's start with some basics. There's two basic inequalities that need to be in each one of these. When X is talking about the number of chairs made, you know you can't make a negative amount of chairs, so we'll say X has to be greater than or equal to 0. Because it's true that they could make no chairs. Right, so greater than or equal to 0. And we obviously understand that they're going to be integers, like they're not going to make like 1.5 chairs. That's kind of common sense. Like the number of chairs they're going to make is going to be positive or 0. Same thing with the number of desks. So when we're writing our system of inequalities, those are the two basics right there. Okay? Now, the other inequalities, they totally come from this table that we made right here. It's kind of like this is a matrix, to be quite honest with you. We're going to put an X next to these because chairs stand for X. We're going to put a Y next to these because Y stands for desk. And there's our total number, so I know 4X plus 8Y. And then I need to decide what kind of inequality symbol I need to put here. Has to relate to 8,000 right here. Okay, so when they say that there's enough carpenters to work for up to 8,000 worker hours, it means they can only work 8,000 or less, right? So it could be less than or equal to 8,000 because they can't work more hours than that, then they'd go into overtime, and that's a whole different situation, and that's the story. So that's less than or equal to 8,000. Then we do that finishers inequality right here. Again, we just throw our X next to this guy, plus 1Y, and again they can only work for a maximum of 1,300, so that's less than or equal to 1,300, and put a little bracket around it because that's our system of inequalities right there. Cool. Alright, so you might also notice I'm using different colors here. The blue ones excuse me, the blue ones, when we graph these lines over here, they're pretty obvious, but I have a green guy and a red guy. You might grab yourself 2 different highlighters. Actually, you'll need 3 different highlighters. 3 different highlighters, and like highlight this inequality one color, I don't care what color, and this one a different color, because it's going to make looking at this graph a whole lot easier to deal with. So what we want to do is like graph this situation. Alright, well, I'm going to label my axes. I already know that X is the number of chairs made, and Y is the number of desks made, so get that labeled. Again, pause the video if I'm moving too fast for you. And now, the tricky part is like, okay, I want to graph these guys. I need to pick a scale, right? And it's like, okay, you just can't count by ones because you need to know some very critical values. You want to make sure you graph the entire feasible region of where all these places intersect, because remember, we're going to graph and shade and find the feasible region. So the best way to do that is to make a little table of values to find your x-intercepts and your y-intercepts. See, these, the green guy and the red guy, they're in standard form, and we could find x and y intercepts real easy. So whatever color you highlighted this guy right here, let's make a little bitty baby table in that same color. So you can make it and then just like highlight it that color or whatever. Okay? And all we need to do is find the x-intercept and the y-intercept. So let's find the x-intercept first. To find the x-intercept, you let y equal 0. So I'm going to put 0 in there. And that means if I substitute 0 in for y, like this would totally go away. Like that 8 times 0 is 0. And then you just end up dividing to find your x-intercept. 8,000 divided by 4 is going to give me 200. So this totally tells me that my x-intercept is 200. Then to find the y-intercept, you let x equal 0, and you would end up dividing that by 8 in that situation. So 8,000 divided by 8 is 1,000, sorry. So basically, found my x-intercept and my y-intercept of the green graph right here. Now I want to do the same thing for the red guy. Make a little baby table of values. And whatever color you highlighted it, it's cool to highlight that same color. It's just, I like to color coordinate. I'm that kind of dude. So to find the x-intercept, I'm going to let y equal 0. If I let y equal 0, that would go away, like doing that cover-up method. And you take 1,300 divided by this coefficient of 2, and you'd get 650. And now I'll let x equal 0 so I can find the y-intercept. And if that's gone, that means the y-intercept is 1,300. This step right here in finding these x-intercepts is super duper important because that is totally going to allow you to find the correct scale. How is that helpful? Well, here's the easy way to figure it out. Let's just do let's concentrate on the x scale. Like, what should I count by on my x-axis scale right here? Well, you look in the x category of all your little tables of values here and find the biggest number. You got a 200, a 0, a 650, and a 0. 650 is obviously the biggest number. That means I have to get up to 650 for sure. Wait a minute, that's 2,000. I made a small mistake. This x-intercept should be 2,000. 8,000 divided by 4 is 2,000. I'm sorry, I missed a 0 in that situation. So, my bad. I'm glad I caught myself. So, sorry. Again, I screwed up here. When I substitute 0, that should have been 2,000, not 200. So, let me refresh. To find the x-axis scale, I totally want to find the biggest number in the list, which is 2,000, right? So I have to get up to 2,000, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 spaces available. Count by ones isn't going to do it, so 100s, I should say, isn't going to do it, so I'm going to count by 200s. I totally counted by 200s just so I could get myself up to 2,000 on this scale. So like I said, if you need to pause the video to get that labeled, get that labeled. Then, similarly, in your y column, the biggest number you got to get to is 1,300. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces available. Can't make it by counting by 100s. So again, I counted by 200s just to get that made. Okay, so get that video paused to get that scale label. Please label all the way up, even though you only need to get to 1,300. Finish it all the way up. Okay, now I'm going to graph these guys. So, truthfully, all 4 of these guys need to get graphed. So if I graph x greater than or equal to 0, that's going to be this guy right here. He's a solid line. And remember, you'd shade him, but I'm going to wait to shade till I'm all done. So he'd be shaded to the right. You know, greater than or equal to, I'm going to shade to the right. Then when I graph y greater than or equal to 0, it'd be this horizontal line, and he'd be shaded above. So this guy's all shaded above, and that guy's all shaded to the right. Please use a straight edge to draw your lines. And now to graph the green guy, we were going to have to do this anyway, right? To graph the green guy, since he's in standard form, it is so much easier to graph this by using the x and y intercepts. Like, there's no need to put this in slope-intercept form. It would just be a waste of time. We've got 2 points on this line already. So green guy, I can plot 2,000, 0, which is right here. Boot, 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 boot. And 0, 1,000, which is right here. Boom. And he needs to be a solid segment when we connect him together. And he should be shaded below that because this is a less than. So shade less than. Cool. Again, if I'm moving too fast, pause the video. Then the red guy, oh, highlight this guy the same color that you highlighted him also, right? The other two are kind of pretty obvious. It's the x-axis and the y-axis, but highlight this guy green or whatever color you were using. Then this guy, plot his intercepts. You got 650, 0 in red, so 650. Notice that's not on one of the scale marks, so when you plot him, you got to guess, and then you need to label him due to the fact that we don't really know where he was. We totally know that's at 2000 because we put him on an intersection point of the grid, so label that point since you had to rough guess him. And 0, 1300, 1300 also, even though he is right smack dab in the middle, we can't tell that from guessing, so label him and then graph that dude. Solid segment, color him the same color that you had this guy, and since he's less than, he should be shaded below also. Alright, now the whole point of this is to find this feasible dang it, find this feasible region. That's where all the shading should be. So I'm going to grab my highlighter and realize, remember I had to be to the right of this guy, and I have to be above this blue guy right here, below this and below this. My feasible region, should get a thinner highlighter, is right meow in this situation. So this is very, 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 very helpful. This is where the linear programming theorem comes in, is this feasible region, the vertices of it are highly important. So that is what step 5 is all about right here. Find and label the vertices. So it doesn't really matter what you call them, but there are 4 vertices right here. 1, 2, 3, 4. Remember, you're going to get a convex polygon in this situation. So those are the vertices. Let's just kind of pick them as we go around and label them as we go. So I'm going to put a big fatty boom batty dot here in pencil and call that A. And then I need to know where his ordered pair is. Well, A is at 0, 1000. And now the next guy is right here. Let's call him B. Notice I don't really know where that guy is at, but he is where the red line and the green line intersect, at least in my colors. That's why I feel color coordinating these is very, very helpful. And what I would need to do is solve the system of equations, or excuse me, I treat it as system of equations and solve this. Well, folks, that's where the matrix is going to come in big time. What I'll do is it's just these two bad boys that I care about in creating this matrix right here. So I don't need you to write the augmented matrix. It's pretty obvious. It's a 2 by 3, and here's all our coefficients. So let's solve that system. Let me clear this out. Let's go to second matrix, and I want a 2 by 3, and I want to edit it and get down in there. And I'm just going to type all those coefficients of 4, 8, 8000, 2, 1, 1300. And then quit out of it, do some math on it. Option B, reduced row echelon form, if my calculator would do it. Here we go. And choose that matrix. And boom! I would like you to write this solutions matrix down right over here to the side, like so. Whoops. Like so. So that was 1, 0, what was it, 200, and 0, 1, 900. That totally means that these guys intersect at the ordered pair 200, 900. So I'll put that in my graph, 200, 900, and I'll put that up here. Vertex B was at 200, 900. Then the other vertex of this region is right here. Call him C. He's at 650, 0. So C is at 650, 0. And then the final vertex is right here. We'll call him D. He's at 0, 0. So let's notice who's not vertices. Like there's where some people have been making mistakes. They think all of these points right here should be vertices. Like they feel that this guy should be a vertex and this guy should be a vertex. Notice he's not a part of the orange polygon, right? The orange polygon has 4 different vertices right here. and I labeled them A, B, C, and D and listed where their ordered pairs were. So, boom. Now, to use the linear programming theorem, before we can deal with that, we're going to use these vertices. We need to write an equation to maximize or minimize the costs. So we're talking about profit. So I'm going to do the profit as an ordered pair of x, y will equal. That's where we go back to the story that they tell us. Let me go back. The story, and they give us those numbers. It says the company earns a profit of $15 for each chair and $20 for each desk. And remember, we let chairs be X and desks be 20. So that's why our profit will totally be $15 for every chair and $20 for each desk. Boom, right there. So the final move is to apply the linear programming theorem and interpret the results. All that really means is we've got to take these four vertices right here and substitute them into this profit equation. So let's do the profit of point A, which is 0, 1,000. Meaning, put 0 in for X and 1,000 in for Y and see what you get. So 0 times 15 is nothing, and 1,000 times 20 is 20,000. So, boom, $20,000. Let's see what that really means. It means if they made 0 chairs, right, because X stands for chairs, and they made 1,000 desks right there, they would profit $20,000. Like, that is totally a possibility for them. Like, to make no chairs whatsoever and 1,000 desks, they'd make a profit of $20,000. Well, let's see what happens if we test point B. Point B is 200, 900. So I need to put those in. 15 times 200 plus 20 times 900. And that means I get a profit of $21,000 in that situation right there. So right there, you can see that that's a better deal right there. Instead of making no chairs and 1,000 desks, it's like, hey, we can make 200 chairs and 900 desks, and we'd make more money in that situation. That's $21,000. Well, let's see what happens. You got to do all the points. So the profit of 650 chairs and no desks whatsoever. So that's basically going to be 15 times 650. And that's $9,750. So that is totally a horrible option. They don't make near as much money. And then finally, it seems a little trivial to do it, but they could make no chairs and no desks, and they would make no dollars in that situation. So these are the four vertices of that situation that they wanted us to test, because that's what the linear programming theorem says. It says, hey man, the maximum or the minimum profit is going to occur at one of these vertices. Like, the mathematician figured that out for us. Now we just got to figure out who's our winner. It's right here. Bing! This is to maximize our profit. So we will put that in a complete sentence. Here's our complete sentence. To maximize the profit, and then since the name of this company is called Built-Right, we're going to totally bring them in. To maximize the profit, Built-Right should produce 200 chairs and 900 desks, and then tell me what the profit was for a maximum profit of $21,000. So complete sentence, capital letter, period. To maximize the profit, Built-Right should produce 200 chairs and 900 desks for a profit of $21,000. Holy mackerel, that was a heck of a problem. Let's do another one and realize it's really not as complicated as you think it is. So, we got to read for a general overview. Robin takes vitamin pills each day. She wants at least 16 units of vitamin A, 5 units of vitamin B1, and at least 20 units of vitamin C. She can choose between red pills, costing 10 cents each. So, notice this keyword, costing. Right, costing 10 cents each, so just kind of focus on that for a little bit. Then contain 8 units of A, 1 unit B1, and 2 units of C. Blue pills costing 20 cents each contain 2 units of A, 1 unit of B1, and 7 units of C. Question time, how many of each pill, bing, how many of each pill should she buy to minimize her cost? So there's a reason, since I've done this problem already ahead of time, why I kind of underlined the cost, because the cost is going to come in later. Just like in the previous problem, the profit kind of came in later. Like these 10 cents and 20 cents aren't going to have anything to do with this little table we're going to set up. They come in when we write our cost equation. So I still feel that doing step 2 first, identifying the variables, is our first move. They are asking us how many of each pill. Bing! Right there. So I got to go back and figure out what kind of pills they were talking about. You know, it's not vitamin A pills or vitamin B pills or any of that. You got red pills, right? So red pills and blue pills. So just going back and reading for detail, there's our two variables right there. So I'll let x equal the number of red pills. Don't just let x equal red pills, right? Accurately defined. And y equal the number of blue pills. And that right there is going to be the tops of our table. So, boom, we've got a red, we've got a blue, and then we'll have that total category again. So, knowing that those are the tops of our little table restraints, what the heck else did they talk about? We're saving this stuff for later. That's for later because that's our cost stuff. Didn't they talk about 3 different things? You had vitamin A, you had vitamin B1, and you had vitamin C. So, they're coming down here. A, B1, and C. And notice, I'm not going to put that little grid anymore. It's up to you if you want to do that. I just don't feel it's necessary, but your choice. So, let's go back, and now that I have the boundaries of my little table figured out, let's start putting some information back in here. So, she wants at least 16 units of vitamin A, right? So that's like a total number for vitamin A. So 16 is a total number because that's what she wants total. At least 16 units of vitamin A. At least 5 units of vitamin B1 and 20 units, that's twice, 20 units of vitamin C. So those are all our total numbers. Alright, so the 10 cents is coming later, and it says that each, so we're talking about red pills here, so here's red pills. They contain 8 units of A, so red pills, they contain 8 units of A, cool, 1 unit of B1, so I'm working down this time, 1 unit of B1, and 2 units of C. So all of this information was about red pills. Blue pills cost 20 cents each. That'll come later. They contain 2 units of A, boom, 1 unit of B1, boom, and 7 units of C. So let's refresh one more time of how we made this table, because that's the biggest question. It's like, how did you know what goes where in the table? By doing this first. Wing! Figuring out the variables. Red pills and blue pills, those go at the top with a total, right? So red, blue, total. Everything else down the side. Then you just got to read for detail on where all the numbers go. So to write a system of inequalities, again, the basics, x has to be greater than or equal to 0, because the number of red pills you're talking about, that's what x stands for. You can't have negative pills. You can get no pills, 1 pill, 2 pill. They're always considered to be integers also. And y has got to be greater than or equal to 0. Then the other inequalities will just be what this table is all about. So I'm going to do them in different colors again. So you've got 8x plus 2y, and then a symbol, 16. The symbol you have to figure out for yourself. She wants at least 16 units of vitamin A. And at least means you can have greater than or equal to that. So at least, because it's cool if she has more, right? Then the other inequality will be the next guy, x plus y greater than or equal to 5, because she wants at least 5 units. And then the last dude will be 2x plus 7y greater than or equal to 20. All of the symbols should be the same once you figure out these in the problems that we're doing, because she wants at least 20 units of that. Throw a big old honker bracket around it also. Cool. Now, to graph this, again, These two purple dudes are pretty trivial. We know where they're at. They're the boundaries, the x-axis and the y-axis, so I don't even graph them anymore. It's up to you if you want to graph them. I need to figure out my intercepts on all three of these, so highlight one of these a color, right? Color, 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 and now I'll do my green guy. Before I can even put a scale, I need to know what I got to go up to. So I'm going to let y equals 0 in this first dude right here. And if I let y equals 0, this would go away. I'd have to take 16 and divide it by 8, and I'd get a 2 in that situation. And now to let x equals 0 in the green equation, y would turn out to be 8. So there's my x-intercepts and y-intercepts for that situation. Red guy, x, y. That'd be, if I let y equals 0, that'd be 5. And if I let x equals 0, that'd be 5. And then blue guy, x, y. Let y equal 0. 20 divided by 2 is 10. Let x equal 0. 27ths. We'll go ahead and just do a decimal because it's easier to graph. So 20 divided by 7. About 2.9. So I'll literally put about 2.9 in that situation. Now it's time to label our axes and come up with our scale. So x's, you look through all your little baby tables, right? In the x category, who's the biggest number? You got a 2, a 5, and a 10. I got to get up to 10. I can make it if I count by ones. So awesome. I can make it if I count by ones. Don't forget to label your axes. Number of red pills on x, number of blue pills on y. On the y-axis scale, 8, 5, and about 2.9, so I can make it if I count by ones also. I will let you pause that video and get all of this made for me real quick. Sweet. So now time to graph. Again, I'm not going to graph the blue ones at all because I know that they're the axes. Green guy. Start with intercepts. So green 2, 0, boom, 0, 8, boom. Solid situation, and connect, and now it's going to be shaded above because it's a greater than, so shade, shade, shade. Little helper arrows help me tell me where I'm going to shade. Color that guy the same color as this one. It's going to help later, trust me. Red guy, intercepts of 5, 0 and 0, 5, so 5, 0, 0, 5, connect, boom, and shade above. And again, you can always pause when I'm moving too fast for you here. And the purple guy, he's got intercepts of 10, 0, and 0 about 2.9. So since that one's not on a nice little grid mark, I'll say 0, 2.9 approximately, and I will connect. And that guy's shaded above. So now, once we've got that all made, let's graph our feasible region. And you don't need to highlight this, in my opinion. You can if you want to. You can just shade it with your pencil, you know. It's up to you. But remember, we've got to use the x-axis and the y-axis as boundaries also because of these guys that we really didn't graph. So you got to stay to the right of this guy, and above that guy, and above that guy, and above that guy. Our feasible region is basically right there. Then we highlight all of this or shade it with your pencil. Just do a light shade. Don't waste a lot of lead. Alright, so I just highlight because it's easier for me to see when can I have all these colors. So nice. Find and label the vertices. So the vertices of this polygon are, here's one of them right here. It's boom. Here's another one. Let's call him B. Here's another one. C, and here's another one, D. It's like all of these corner type places. So A, B, C, and D. Found A already. He's obvious. He's at 8, 0. This is why I like the color, because to find B, B is where the red and the green are intersecting each other, and it kind of looks like they're intersecting at 1, 4. But it also kind of doesn't look like they're intersecting at 1, 4. There's only one way to know for sure if they intersect at 1, 4 or not, and that is to solve the system between the green guy and the red guy. So thank you, Mr. Matrix. That's where that's going to come in. I'm going to let the matrix do the work for me. by putting those coefficients in. So I'm doing green and red. That's why I like the color, so I can tell which ones I'm dealing with. 8, 2, come on, 16, 1, 1, 5, quit, and then go do the reduced row echelon form on him. And yep, he did intersect at 1, 4, but since we used a matrix, I want that off to the side. 1, 0, 1, 0, 1, 4. So B is at 1, 4. C, that one is a definite right there. At least on my graph, he's at 3, 2. So got him going for me at C at 3, 2. So if it's a definite and you know it's there for sure, dude, it's like, hey, I don't need to solve the system. But if you did, it's between the red guy and the purple guy, so you'd have to solve that system. And D is at 10, 0. So let's write our cost equation. Our cost equation, that's where we go back to the story and find those cost numbers. Remember, here's the cost of 10 cents and the cost of 20 cents. So we'll use a C for cost. C of xy, the cost of x comma y, will equal, it's 10 cents for a red pill, and remember red pills were x, so 0.10x plus 20 cents for a blue pill. Cute. And now let's use the linear programming theorem. So we just substitute all of these guys in. The not profit, I do that all the time. It's the cost of 8 red pills and 0 blue pills. You just substitute those in. And 8 times 10 cents, that would give you 80 cents. All right, so 80 cents is written like this. It's not 0.80 with a cent sign, it's $0.80, which we call that 80 cents. Substitute the rest of these in, B, C, and D, into this cost equation and find them for me. So I got the cost of 1 red pill and 4 blue pills to be $1.60. The cost of 3 red pills and 2 blue pills to be 70 cents. And the cost of 10 red pills and 0 blue pills to be $1. Let me tell you something. I knew something seemed a little fishy. I made a mistake. This is not at 80. He is at 08. You goofy guy. A is at 08, not 80. And at 08, that would have been not 80 cents, but 20 cents times 8 points 2 times 8, $1.60. Sorry about that, folks. Okay, but anyway, to minimize the cost, it was still this blue guy right here. That is the cheapest one of all of these situations. So 70 cents. So in a complete sentence, to minimize her cost, Robin should buy 3 red pills and 2 blue pills each day for a cost of 70 cents. Alright, that's 2 of them. Let's try another. So let's read this for a general overview. Furniture manufacturer makes upholstered chairs and sofas. On the average, it takes carpenters 7 hours to build a chair and 4 hours to build a sofa. There's enough carpenters for no more than 133 worker hours per day. Upholsterers average 2 hours per chair and 6 hours per sofa. Enough upholsterers for no more than 72 work hours per day. The profit for each chair is $80, and the profit for each sofa is $70. How many chairs and how many sofas and chairs should be made to maximize the profit? So this is very much like our first problem. Let's identify the variables. I let x equal chairs and y equal sofas, because that's the order that they gave them to me in here. They kind of switched the order around down here. It really doesn't matter which one's which as long as the numbers go in the right place. So since x was chairs, the number of chairs, and y was the number of sofas, those are the top categories in my little table, and I need a little total guy. The other question is, who are these, or what should be over here? Well, that's the other ingredients. You got carpenters, and you got yourself upholsterers. So, boom, carpenters and upholsterers. Why don't you pause the video and see if you can get all the numbers in this chart correct for me. So the total hours for a carpenter is 133, right? It took them 7 hours to build a chair and 4 hours for a sofa. And down here, those numbers accordingly. System, real simple again. Boom, you know you need your basics. The number of chairs has to be greater than or equal to 0. The number of sofas has to be greater than or equal to 0. Then you go across in the old chart right here. And why does the symbol have to be less than or equal to? Because they can work no more than 133 worker hours per day. And same thing down here, no more than. So let's make ourselves a graph. I'll need my intercepts. Again, red guys we don't care about. Let's go with the green guy to find my intercepts. Come on, Ben. Work. Sorry about that. X, Y. I'll let Y equals 0 here. Then I need 133 divided by 7. So let's see what that turns out to be. That's a 19. And then if I let x equal 0, 133 divided by 4, it'll give me a decimal, but that's fine. That'd be 33.25. And then on the blue one, boot, let y equals 0, 72 divided by 2 would give you 36. And then let x equal 0, and that would give you a 12. Nice. So now label our axes, right? So x is the number of chairs and y is the number of sofas. And let's figure out what I got to get up to in the x-axis column. Got to get up to 36. So I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 spots available. Whatever I got to get up to, 36, which is that case, if you split it up 13 ways, you can figure out what you need to count by. So you got to count by more than this. So if you round up to 3, it's fine if you want to count by 3s. You could also round up to 4 if you wanted to count by 4s. But I try to look at the other numbers that I'm going to plot on, you know, and it's like, okay, if they were all multiples of 4, like 36 is a multiple of 4, and 19, if that was a multiple of 4, that'd be nice. Or maybe if they were all multiples of 3s, it really doesn't matter what you count by. So I would count it by 3s, right, to try to maximize this. And then the number of sofas. I got to get up to 33.25, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots available. So that would be 3.325, round up to 4s. So I totally could count by 4s if I wanted to. I just went ahead and counted by 5s because it's a little easier to count by 5s. So it doesn't matter. You count by 4s, you count by 5s. It's up to you. Cool. Now the simple part, we got all of it done already. To graph these guys, the red ones, remember that's your x-axis and your y-axis. The green guy, let's plot those intercepts of 19, 0. So 19, 0. Since that's not on a grid mark, I'm going to literally label him as 19, 0 and 0, 33.25. So yeah, 0, 33.25. See, a lot of people think these are the vertices right away. You don't know if those are vertices or not. That's why we got to graph the feasible region. So, boom. And that's got to be shaded below because of the less than. Blue dude, plotting his intercepts. 36, he's a nice, neat place. 12, not quite on there. So, 0, 12. Connect. And that's got to get shaded below. And now, to find the feasible region, we are going to shade that in. Remember, we had to stay to the right of this, above that, below the blue line, and below the green line. And our vertices are right here. A, B, doesn't matter which one's which, that's why we're labeling them, C, and D. So we will list them all out. A is most def at 0, 12. B, I don't know. So I got to find myself a system to solve that's between the green line and the blue line. So I will let you do a matrix to solve that. Why don't you pause the video, solve that. And please please write your solutions matrix after you do that. Notice I kind of like said, here's what I'm doing. These are the two guys, and that's going to be for vertice B. Here's my matrix. I found him at 15.7. C is obviously, oops, my bad. C is obviously at 19.0, and D was obviously at 0.0. So B, C. Cool. So these four vertices are the guys we got to test in the equation we're about to write here. It is a profit equation. So remember, we're going to use a P for profits. The profit of x comma y will equal x stands for the number of chairs, so $80 per chair and $70 per sofa. And now let's test those. So why don't you do that? Please pause the video, test all 4 points. We're going to do the profit of 0.12, which I actually listed correctly this time. The profit of all of them. Please pause the video, get that done for me. Hopefully you came up with these numbers right here. And we're trying to maximize the profit. So which one of these bad boys gives me the biggest profit? Well, that would be the blue one right here. If we made 15 chairs, because x is 15, and 7 sofas. So we'll write ourselves a complete sentence here. To maximize the profit, the company should produce 15 chairs and 7 sofas for a profit of $1,690. Period. Cool. So here's what we're doing in class. On the next guy, I turned him loose. So I would like you on the video, or I won't necessarily turn you completely loose. I want you to get these 3 steps done right here. Read this problem, do all 3 steps. I do step 2 first. Like I said, identify the variables, make yourself a table, write yourself a system. Here's what you should have, in my opinion, and put the cool little bracket around here. So just checking ourselves before we go too much further. And now to graph, let's find our intercepts. Right, find the intercepts and make our scale. So please get that done. Pause the video, give that a shot. Here's my intercepts right here, and I labeled my axes. Ounces of brand A and ounces of brand B, and I had to get up to 400. So I really kind of counted by 50s and went every other one. And this guy had to get up to basically 600, so counted by hundreds. Time to graph it, find a feasible region. Get that done. That's what I came up with for the feasible region, and now for the vertices. So I will let you do the vertices. There's what I got, A, B, and C. I had to solve a system on the blue guy and the red guy, so I let the matrix do that work. Thank you, matrices, because, man, I hate solving systems by hand with all those crazy decimals. It's just so messy. Cost equation also, got him. And finally, I will let you do the linear programming theorem on all 3 of these vertices to see which one of these minimizes the cost. Don't assume that it's always this one, you know. I mean, you're right, most of the time it is, but it's not always the case. Sometimes it's one of the other vertices. So, got to show all the work anyway. So, I'll let you pause that video and see what we got. Here's all 3 costs, and the one that minimized the cost, right, because that's what they're asking, is the green guy. So to minimize the cost, I wrote that in a complete sentence. So folks, it's really not as bad as it seems. It's a lot of information, there's no doubt about it, but one move at a time, and I think you can handle it. So let us know if you have any questions. Have a good one.